All right, we're back in Calc 1, Chapter 2, Section 4, Part 2, as I'm calling this, where we're going to talk about limits as we approach from the left and from the right, and limits that when we evaluate them, they tend toward positive and negative infinity. And really, if I'm going to keep making videos in this office, I have to get better lights. I look ill. Let's make me small. There we go. So here's the formal definition of what this author calls a left-hand limit. We're approaching from the left. You can see here that our limit statement says that we're approaching from the left or from the negative side. And in order to be able to say this, or I should say, if I just read this slide says we can say this thing that I've circled, that the limit as x approaches a from the left of f of x is equal to L, if for every number epsilon greater than 0, and remember that epsilon represents that, it used to be a plus or minus in the y direction, but in this case it's going to be, as a left-handed limit, epsilon is still going to be a plus or minus because we still want the limit to be approaching a particular y value. However, for every number epsilon greater than 0, we'll need to be able to find a number delta that's greater than 0 so that our x values are approaching from the left. So we've got that a value, which is what our limit is approaching as x approaches a from the left. How far from the left would it be acceptable for us to approach from? The answer to that question is going to be delta. And why are we choosing a particular delta value? So that as we approach from within some reasonable distance from the left of our a value, our y values will all be grouped within some reasonable margin of error in the vertical direction, which is what our epsilon value represents. And this tells us that the result of our efforts with delta need to be that our y values stay within epsilon of our limit, L. There is also a definition as we approach from the right-hand side, and you see that this says a plus delta instead of a minus delta. Otherwise, this statement is the same. We're still within plus or minus epsilon from our L value. And the other small difference in here, this plus sign is what tells us that we're approaching from the right. And let's have an example. In this example, we are working with the square root function, and our x values are approaching 0 from the right, which makes sense because the square root function arcs out like this, and it is defined at 0, 0. So we wouldn't want to be approaching 0 from the left because there's nothing going on over there. And we're going to utilize that formal definition in order to prove that this is a reasonable statement. So epsilon here is going to be a positive number. They're not telling us what it is. They're just telling us that there's an epsilon. Our a value is 0. That's what our x value is approaching. Our limit we believe to be 0, that's what we're proving. So we want to find a number delta so that some small delta will compel our y values to be within some small distance away from 0. I'll say that one more time. These delta values over here are going to compel our y value, that's f of x, or it's our y value, will compel our y value to be within some small distance away from our lowercase a value of 0. This statement with all these arrows on it can be cleaned up a bit. Certainly the absolute value of x minus 0 can be simplified to the absolute, or to just the square root of x, but where did the absolute value bars go? We're going to assume that if we're taking the absolute value, the square root of x, that we're going to use the positive result. You might be asking, well, I thought the square root of 9 was plus or minus 3 by the square root property. You're right, but if we used the plus or minus for all of those answers to the square root property, we would end up with a graph that looks like this. This is not the graph of a function. It fails the vertical line test, and that's why we're only going to be using the positive results, so that we only use this positive half of the square root graph, so that it is the graph of a function. So I don't need to take the absolute value because I know that all these values are going to be positive because we're working with it as a function. All right, and if we square both sides of that statement, epsilon is positive, the square root of x is positive. I've squared both sides, now I have x is less than epsilon squared. And surely x is going to be strictly positive. It's going to be greater than 0. And so you can see, this doesn't necessarily just jump out at you, but after a while it will. X is less than something, x is less than something. I think we know what delta is. We've just modified our epsilon statement to the point where it matches up well enough with our delta statement that we can sort of do a swap or a substitution and realize what our delta value should be. It should be epsilon squared. The strange part is, especially if you've done algebra and geometry and pre-calc with some trig in it, and here you are in Calc 1, and the answer to this question is delta equals epsilon squared. It's a very generalized answer, and it's an answer that allows for modifications to the epsilon value. So if we decide that we want to narrow our target or refine our target, then we will need to be refining our input values and decreasing that margin. And so that's why we have these delta epsilon proofs, is so that we have the ability to make those modifications. Now if we take epsilon and we send it off towards 0, then we're going to really have to tighten down on our delta values, and that's ultimately what delivers us to the proof, which allows us to make these limit statements that we've been making recently. This is a process in these example problems where we then take the supposed delta value that we've just discovered and we plug it back in order to illustrate that it does indeed work. This is not something I'm going to spend time on, but that is an illustration of the fact that it works. It's like when you solve an equation for x, and then you take those x values and plug them back into the equation to make sure that they work. All right, so that's what was happening on that previous slide. Here, I think that this slide just wandered in from our limit laws conversation, but everything that's on this slide is true. The limit of the sum is equal to the sum of the limits. And then here's an example problem. Do I want to be working on this example problem? I think what I want mostly to tell you here is that as you continue reading these, you should be able to identify the components. And this entire statement is about x values, and this entire statement is about y values. And then let's look at some of the details of it. Is my pen going to work? Here we go. The limit as x approaches a applied to our function f of x, and the answer is going to be capital L. These x values, well, the a value is this number right here. And the x values that are getting closer and closer to a are these x values. And we want to if here's the number 1 on our x-axis, we only want to be using certain x values that are within plus or minus delta, away from the number 1. So that's where our x values are going to be coming from. That's obviously the delta. And then this is our function. And this is capital L. We want to make sure that our y values are within an epsilon value of 0.1 away from our capital L value, our limit value, which in this case is 0.4. So on the vertical axis, if this is 1 up here, then maybe this is where 0.4 is, right here, and we want to be within plus or minus 0.1, so our y values want to be in here, between 0.3 and 0.5. So just continuing to practice reading these things and what it is that they're looking for. You could most definitely graph by hand and do some algebra in order to determine where the point of intersection, let's see, this was 0.4 plus 1 makes this 0.5. 0.4 is roughly here. 0.3 is right here, this horizontal black line. And by hand, you could do some horrible algebra and find the point of intersection right here. You know what the y value is, so you plug that in, you solve for x. You take that x value and you drop it down here, and then you take the y value of 0.3 and you plug it in, and you zero out one side of the equation and you solve for x, and you get the corresponding y value that drops down to here. And we know that the x value was approaching +1. So somewhere in here, perhaps here, is +1. So we have to decide, are we going to use this distance or this distance as our delta value? And of course we would use the smaller of the two. That determination will be easy to make. The tough part is, once you have your y values from the plus or minus epsilon, trying to figure out the corresponding x values for these points on our original function, depending on the function, that can be a real nightmare. So if the function is really nasty, like this one's kind of nasty, the easiest way to do this would be to plug in your original function f of x into Desmos, desmos.com, a free online graphing utility, and also graph y equals 0.5 and y equals 0.3, and just click on the points of intersection in order to discover the x coordinates of those points. The other option is to, if you have a TI graphing calculator, you could graph those same three equations, your original function and y equals 0.5 and y equals 0.3, and use the trace button and second trace, which puts you into calc mode, and then you could select intersect, and you should watch a video on how to do that if you would like to learn how to find the intersection of two functions using your TI graphing calculator. It's not difficult. That video should be like a minute long. Right, and then once you have those x values, in this case, the x values that we discovered are 2, and this is 1, and then this other x value that we found was 0.67, or 2/3, and so the difference from here to here is 0.33, and the difference from here to here is 1. The 1 is too big, so we're going to keep the 0.33 and set that equal to our delta value. It's that easy. I'm hoping that that was funny, or I'm hoping that you agree that it's that easy. I'm telling you though, if you do a handful of these, you're going to get to the point where you're just going to be bored. It's just a very mechanical process that you can go through in order to find these delta values. Precise definition of an infinite limit. So here what's happening is we're working with x values that are within delta of some particular a value. Yes, it's still this a value. And as a result of keeping our x values within plus or minus delta from a, the result will be y values that are larger than some predefined y value. So we're not trying to keep our function's output values within plus or minus epsilon anymore. We're trying to keep our y values above some sort of a threshold. And we're going to see an example of that graphically here. So you'll notice that along the x-axis, we have our a value. X is approaching a. We saw that in our limit. You see the plus and minus delta, giving us our interval worth of x values that we can work with. And as long as we pick an x value that's in here somewhere between those two vertical kind of orange mustardy colored lines, as long as we're picking an x value from in here, let's pick one. Let's pick this one right here. I don't have a straight edge, so this is going to be kind of a wobbly line. But if we take that x value and we follow it up here, we end up at a point on our curve that has a y value greater than m. So that's what's going to happen. We're going to be given an m value, and our goal is to surpass that m value by constraining our x values around a. And the process for that is very similar. This is just an articulation of what we were just talking about. If the m value gets larger, then the delta value will probably need to be smaller. The graph that we were just looking at, if it wasn't the graph of 1 over x squared, the graph of 1 over x squared will look a lot like that. And here's a solution to proving that it's reasonable for us to say this. Again, we're choosing these x values that are plus or minus delta away from 0, because our limit is approaching, our x values are approaching 0 in our limit statement. Then, if we can find a delta value that constrains our x values enough, then our y value will be greater than m. We're just sitting around waiting for somebody to give us an m value, and then we'll really be able to dial in on a delta value. But for the moment, we're going to work it in a sort of a generic fashion. So we know that we want our y values to be greater than m, and if I multiply both sides of that inequality by x squared and divide both sides of it by m, I end up with this statement. Don't worry about switching the sign, because x squared is for sure going to be positive, so 1 over x squared is definitely going to be positive, and m is given to be a positive number, so we don't have to worry about switching the sign. Now what am I going to do? Now I'm going to go into here and I'm going to take the square root of both sides, and after I simplify both sides of that inequality, I end up with this. We're square rooting an even power, and so we do need to use these absolute value bars, and yeah, so the absolute value of x is going to be less than. We've just taken the square root symbol and distributed it to the numerator and denominator, and the square root of 1 is 1, and we're leaving the radical in the denominator. And what you're seeing, maybe it's jumping out at you at this point. Look at this statement, and then come over here and look at this statement, see the absolute value of x, see the less than symbol, and then you see the difference. One says delta, one says 1 over the square root of m. So guess what we're going to let delta equal? 1 over the square root of m. So it's a bit of a game trying to get the epsilon statement modified to the point where it looks enough like the delta statement, so to speak, that we can make that kind of a substitution, allowing us to declare a delta value. It's good times. It's pretty fun. At least you get to do it in the air conditioning. Very similar process when your limit, or you believe that your limit is going to negative infinity. That proof process is almost identical, except here we're trying to keep our output values, our y values, less than some predetermined negative number n. And then these slides are set up for you to have a group quiz and a solution to a group quiz. I will put this quiz question up on the screen if you would like to take a look at it, or screenshot it, write it down, whatever, and then I will move up here to the solution process so that you can take that down or screenshot it, and then don't look at it. Go back up to this previous slide and try to work out your own solution to prove that this limit does indeed go to positive infinity. Make your delta set of statements, make your epsilon set of statements, and then try to modify the epsilon statement to the point where it looks so much like the delta statement or inequality that you're able to make that substitution and declare yourself a delta value. I have faith in you. I think you can do it. And the next time I see you, we will be looking at some homework problems. So I'll see you over there. Thanks.